Howdy PreCal, it is Ms. Kosh, and we are jumping into 3A, graphing and inversing exponential functions. I don't know that inversing is actually a word, but we are going to be taking the inverse of, and that took up too much space to say, taking the inverse of exponential functions. So as we get started, let's look at Desmos to see what our graph, what's happening with these numbers. So if I take 2 and I raise it to the power of x, and I start looking at my table of values, I can... There it goes. I can look, these values, these numbers are getting bigger and bigger and bigger and bigger, and they're getting bigger pretty quickly. Like, it didn't take us long. We're just multiplying each time by 2, but it didn't take us all that long to get to some pretty large numbers. Okay, this would be what we call an exponential growth situation. And let's get rid of that mess. And if I took something like 1/2, so say 0.5, and I raise that to the x, this, let's go look at the table. This is getting... let's do 2, enter. This is getting smaller and smaller and smaller, and pretty quickly. Okay, so you'll notice that none of these values were 0, but they get ridiculously close to 0. I have to zoom in a whole lot. See, look, it's not 0. Okay, so now let's go look at the notes. This would be an exponential decay problem. The general equation for an exponential growth function is f of x equals a times 1 plus r, where the base is the b value, or in this case, it would equal 1 plus r. And a decay, the base is where the base is equal to 1 minus r. We also might say that where if I have b is greater than 1, then it's an exponential growth. So if this b value right here is bigger than 1, it's going to be a growth. If this b value is, between 0 and 1. And we're not really going to look at making b negative is beyond the scope of our course. So anything between 0 and 1 is going to give us an exponential decay. So there's 2 different scenarios. A is our initial amount. Okay, that's what happens if I have a times b to the 0. B to the 0 is equal to 1, so this is just a times 1, which is just a. So often the exponent, b, is often the amount of time that we're considering. It might be something different, but more often than not, it's time. Sometimes in years, sometimes in months, sometimes in days. It'll depend. The r value is the rate of growth or decay. And we'll look at some situations in just a second. Okay. Any quantity that grows or decays by a fixed ratio at regular intervals is said to have an exponential growth or an exponential decay. Okay, so on this first one here, I have 0.7 times 3/2 to the x. What we always want to look at to know is it growth or decay is this b value, the thing that's being raised to our exponent. And 3 over 2, you might also know that that's equal to 1.5, which is bigger than 1, and so this is a growth factor. What's our initial value? Our initial amount is 0.7, but I get lazy and don't write that. Growth or decay factor. Okay, so we had a b value. So our b value, because this is a growth, our b value is going to be equal to 1 plus that growth factor. Our b value, we just said, is 1.5. And so this becomes 1 plus r is equal to 1.5. Therefore, subtract 1, I get 0.5 is equal to r. So our growth factor is 0.5, which we sometimes will see written as, say, 50%. Okay. Oh, wait, I answered the wrong question. This is the rate. Okay, sorry. No, you can go back here. It still is the growth factor. The growth factor, did I say that before? Sorry. The growth factor is 1.5. The rate at which it's growing is the r value. So that b is the growth factor, and it's 1.5. Okay, let's look at the next one. On this one, is it a growth or decay? Well, we're looking at this right here to determine if it's a growth or decay. 1/4 lives between 0 and 1, so this is a decay. Our initial value is 4. Our growth factor is 1/4, which in a second it'll be helpful to think of it as being 0.25. Okay, our rate. So in this one, our b value will be equal to 1 minus that rate. The b value, 0.25, is equal to 1 minus r. So if I subtract 1, I get a negative 0.75 is equal to a negative r. And now I can divide away the negative, and I get my rate is a 0.75 or 75%. And we might say this is a 75% decrease. Okay, maybe I should come back over here, and call this an increase. Okay, the next one, growth or decay. Well, we're looking at our b-value. Our b-value 3 is greater than 1, so this is a growth. Our initial value is the 2. Our growth or decay factor is 3, and so our rate, our b-value, is going to be equal to 1 plus r. Subtract, so b was 3, 1 plus r, subtract 1. We get a rate of 2, which means that leads us to a 200% increase. Okay, the next one right here, I am looking at this number right here. 0.4 lives between 0 and 1, so it's a decay. Our initial value is 1/2. That's that a value out front, right? And the growth or decay factor, so if I take my b value is equal to 1 minus the r value, and so 0.4 is equal to 1 minus r, subtract 1, I get a negative 0.6 is equal to negative r, divide by the negative, I get my growth. I keep doing the rate too soon. The growth or decay factor is 0.4. The rate, it's a decay factor. Did I circle that other one? No, it was a growth factor. Okay, my bad. The rate was what I was just figuring out. The rate is 0.6, which would also be equal to 60%. And this is a 60% decrease. Okay, now let's look at, oh my goodness. So now let's look at what these graphs look like. We saw it a second ago on Desmos. So on the decay factor is where, we have like 1/2 to the x and it's decaying. It starts approaching this asymptote here at y equals 0. And the pattern depends on the base. Okay, so whether it decays or whether it grows depends on this b value. So if you have a b that is greater than 1, expect it to grow like this, but they both have an asymptote at y equals 0. And then this point right here, I don't know who I heard call it this the first time, but they would call it a pivot point. You can kind of see like this is where it starts growing quickly or it starts, so it's kind of, so I don't know, maybe that's why they call it a pivot point. But that point is really helpful to work with. And in the parent function, it shows up at 0, 1. So there's our pivot point. We can have all sorts of transformations to this graph. So we can have a vertical stretch. We can have a horizontal stretch or compression. We can have a horizontal shift left or right. We can have a vertical shift up or down. So this would be up or down. This would be left or right. And this is that horizontal dilation is what I often call that. And this would be a vertical dilation. I'm too lazy to write the word. Okay. So now let's look at some of these examples here. When I have 2 to the x plus 2, it's going to shift my whole graph up 2. When I have 2 to the x minus 3, it's going to shift me down 3. But now when I put the plus 4 in the exponent, that will shift me left 4. Now be careful. I like to say I'm not grading your handwriting, but I'm grading your handwriting. If it is in the exponent, it needs to be in the exponent. Okay. This one, 2 to the x minus 1, is going to shift us right 1. A negative out front is going to reflect over the x-axis. And so if you think about it, if I have an exponential growth that reflects, that's kind of terrible looking, but whatever, but that reflects over the x-axis, it changes my range. So I'm going to have the same asymptote that I would have had otherwise with the parent function. But now, instead of going from the asymptote to positive infinity, I'm going from negative infinity to the asymptote. Okay. The other thing is if I have a negative in the exponent here, and this will reflect me over the y-axis. And what this does is it takes an exponential growth and makes it become an exponential decay. So it doesn't change the domain or range, but it does change the end behavior. And let's talk about this a little bit more. If I have 2 to the negative x, What this could be written as is this is 2 to the negative 1 raised to the x, because when you have power to a power, you multiply. Well, what is 2 to the negative 1? That is 1 over 2 to the x. And so when I take an exponential growth, 2 to the x, and I reflect it over the y-axis and make it, and this goes to 2 to the negative x, what's going to happen is I'm now getting an exponential decay problem. And it works with the properties of exponents, or it works with transformations. So it's always fun when math works multiple ways. I don't think I need that in my notes. Delete. Okay. So now I worked a couple of the examples just to make the video go a little faster. So what I want to look at here is, let's look at this graph. I want to talk you through what my expectations are. We're going to find the y is for the asymptote. And so the asymptote, it would have been at 0, but everything got shifted down 3. Oh, you know what? Let's talk about our transformations. What are our transformations? We went down 3. Okay, so that meant that the asymptote went down 3. Our domain is going to go from negative infinity to positive infinity. Our range is now going to go from that asymptote, negative 3, to positive infinity. And then what I would like you to do, let me split my screen with Desmos. Get rid of that mess. What I would like you to do is figure out where's your pivot point going to be, and then I want in the table, I want 3 points on one side of the pivot point and 3 points on the, I want a 3 and 1 situation. I want 3 points that are nice whole numbers, they're typically whole numbers, and then 1 point that's not typically a whole number. I'll show you what I'm talking about. So in this one, my pivot point starts at, it's initially at 0, 1, and now all I have done in the whole wide world is moved everything down 3. So it moves to, well, 1 minus 3 is negative 2. Okay, so we're going to use that idea to help us figure out what points we want in our, so it's 2 to the, oh no, hang on, what am I doing? That's not what I wanted to do. This is what I wanted to do, 2 to the x. And then if I just start typing in minus 3, notice it moved me down. So if I want that, well, I'll show you in a second. Basically, if I want it in the exponent, I have to put in parentheses. Okay, so let's look at, there's that graph. So it's an exponential growth. What I want to do is I want to look at the table. And so I want you to, we said our pivot point was going to be at 2, I don't need this one, delete. Okay, well, whatever, there it is. Our pivot point is at the point 0, 2. I want 3 points that give me nice whole numbers. Do you see how I have 1, negative 1, 2, positive 1, 3, 5? I want those 3, and then I want you to graph 1 point that's not a nice pretty, that would be that decimal that's on the other side of the pivot point. Okay, so 3 points, if it's an exponential growth, it would be to the right of the, what do we call that? To the right of the pivot point, and 1 point to the left if it's an exponential growth. That'll change if it's an exponential decay. So let's plot those points and let's plot that asymptote. We know we have an asymptote at y equals negative 3. We know we have the point, well, we had the pivot point 0, negative 2. And then from the table, I see 1, negative 1. I see 2, positive 1. I see 3, 1, 2, 3, 4, 5. And now I have this 1 that's not going to be as pretty, so negative 1, negative 2.5 is right here, and then this, okay, my mistake is that this should not be curving back up. Do you see what I'm talking about? It's just kind of hard to be precise. So that is our graph. So what happens as we go to negative infinity? Well, we get closer and closer to the asymptote of negative 3. What happens as we go to infinity? Y also goes to infinity. Okay? So there's that one. Let's look at, here's my lovely graph. On the next one, this was an exponential decay, and I wanted to go a little bit faster. It's going to go, what's this one doing? It's going up 1. So my pivot point had been at 0, 1, and now it's 0, 2. It's an exponential decay. So on this time, I gave you 3 points to the left of the pivot point. So notice I circled the pivot point, and then 1 point to the right of it. So I plotted all of those. There's my asymptote, and I gave you all my details. Okay. You can pause the video here and look a little more closely if you need to. The next one here, we have this one that's, what's it doing? This one is going to move us right 1, and up 2. So our pivot point that starts at 0, 1 has now gone right 1, so it's going to go to 1. It's going to go up 2, so that goes to positive 3. Okay, so I filled out all those details. I found my 3, so I knew my pivot point was going to be at 1. So here was the pivot point. And so I have 3 where they're nice whole numbers, you see what I'm describing, and then there's 1 value on the other side. And so those are I end up plotting 1, 2, 3, 4, 5 points. So I want to see those 5. Okay, let's do this one together. So notice we have seen 2 to the x, we've seen 2 to the x, we've seen 1/2 to the x. Everything we've seen so far, we even saw, I don't know, somewhere, no, we didn't see that. Okay, maybe it was at the beginning when I showed you on Desmos. I used 2 and 1/2. Then now all of a sudden we've got a new number. Okay, so we've got 1/3. You'll notice though that this is still going to be an exponential decay. And we are now going left 2 and down 3. So our pivot point started at 0, 1. We had to go left 2. So it's moving to -2 and then down. Oh, I got rid of the 3. Maybe sometimes I hit the screen accidentally. Okay, 1 going down 2 is also -2. So let's type this into Desmos. Well, my y equals, where's my asymptote? It's at -3. My domain is always all real. As soon as you see it's an exponential function. My range, it's going to go from that asymptote and go up to positive infinity. Then come here, Desmos. Where are you? Go away, go away. I have 1/3. I think it's helpful to put that in parentheses also. Raised to the, okay, now notice if I try and do x and then put +2, it drops it down, so that's no good. So I have to come back up here and use parentheses, x plus 2. Maybe if I, let me see something. I'm just checking here. If I say x and then I go -3, and maybe I can come back in here and say +2. Nope, I need my parentheses. Okay, good to know. Delete, okay, parentheses, x plus 2, close parentheses. Okay, so here's my graph. I want you to find the table. We said the pivot point was going to be at -2. These are giving me too many on the smaller side. So I want 3 before that. So I want -3, -4, -5. So I want -5. I want -4. I want -3. I want -2. I want -1, and that's enough as far as, oh my, that's kind of ridiculous. Well, we're not going to plot 24, obviously. So what is this as a fraction? Will it tell us on here? I mean, it's -2 and 2/3. Okay, so we have -5. Nope, we're not plotting that. We have -4, 6. -1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Let's assume that my vision is somewhat okay. Number -3, 0. -2, -2. -1, and then -2 and 2/3 is going to be somewhere about here. And we forgot to draw in our asymptote, which we knew to be at -3. You like that we collectively forgot? It was just me that forgot. Okay, so here's our graph. Notice this is still an exponential decay situation. We just were kind of decaying faster. Do you see how, well, let's try one more time. Oh, I kind of missed some of those points. Okay, anyway, it is what it is. Okay, so as x goes to -infinity, our y value is going to go to infinity, and as we go to positive infinity, our y value is going to go to our asymptote at -3. Okay, I worked one of the next two. Here it is. This one had a transformation. It had a reflection over the x-axis. So actually, so does the other one. But let's do this one together. We'll do number 9 together. So I see my asymptote is going to be y equals 4. My domain is always -infinity to positive infinity. And now let's see what happens. Okay, so my pivot point starts at 0, 1, and then I reflect over the x-axis. So I go to 0, -1. Okay, so let's start by reflecting. What was here at 0, 1 has now reflected down to 0, -1. Okay, and then we shift. How do we shift? We went left 2, so it was a reflection over the x. We went left 2 and up 4. Okay, so let's take, after our reflection over x, left 2 means I go to -2. Up 4 means -1 plus 4 is 3. And so I have an asymptote at 4. 1, 2, 3, 4. And I have a pivot point at -2, +3, which is right here. So my range, you'll notice I'm below my asymptote. My range is going to go from -infinity to that value 4. Okay, so let's go let our table help us. Come back, Desmos. Where are you? Go away. It doesn't go away when I first, I don't know, maybe I'm just not into the screen yet. I don't know. Okay, -3 raised to the power of, we need parentheses, x plus 2. Close those parentheses, and then +4. And sure enough, it dropped down below. Let's come up and find our table. We wanted, on this one, we're going to have, our pivot point was at -2. Oh, those values get big. Let's also throw in a -3. I thought I hit 3. There you go. Okay, so I can see there's -2. Gave me the point of 3. -1 gives me the point of 1. 0 gave me the point of -5. 1, 2, 3, 4, 5. 2 gave me, oh, that's ridiculously large. We're not going, or 1 is ridiculously large. -3 is 3 2/3, so that's somewhere about here. Okay, so we're going to just plot the ones. So in general, I did say I want 3 and 1 point, but if you can only get 4 points to fit on your grid, that's fine. So you'll notice, what did we do here? Well, now we lost the screen. We started with an exponential growth problem, and then we reflected it over the x-axis. This one we call a growth. Do you know what we call this one? Nothing. We don't call it anything. It's not a decay. It's not a growth. It's just an exponential function. Don't call it anything, okay? But it's an exponential growth that was reflected over the x-axis, but it doesn't have a name. All right, that can go away. So let's go ahead and curve this out. Something like that. See how quickly, oh, I almost hit that point. Let's just make the point a little bit bigger. Oh, okay, sorry. Okay, so as we go to -infinity, our y value is approaching our asymptote. As we go to +infinity, our y value goes to -infinity. On this one over here, what we did is we took an exponential decay. We reflected it over the x-axis, and so it looks something like this. Do you know what we call that graph? Nothing. It has no name. It's an exponential function that's been reflected. There it is. Yes, on this one, it was kind of similar. I followed a similar process and ended up with that graph. Okay, now we're going to practice switching our x and our y values. You know what? This is kind of a long video so far. Let me come back and we'll finish the notes in the next video. All right, like, subscribe, comment, and go practice.